Court. So this week we're going to start talking about, well, we already actually did start talking about it, this thing called electric field. It was the last section of chapter 22. But this chapter, we're going to do a lot of calculations with them and how to actually find the electric field for various shapes. Primarily these four shapes, either if you have a bunch of charges on a rod, a bunch of charges on a plate, or a bunch of charges on a sphere. And cool thing about these shapes is not because they are, especially, fancy shape. It's because they are simple shapes. And that way the mathematics you guys learn in calculus 1 and 2 can be used on them, because we're going to simplify these shapes. Well, these shapes are, the calculations is simple enough so they can actually make calculations with them even with just calc 1 and 2 type of techniques. So that's why we picked these shapes. But before I talk about electric field, I think last week I talked about, people think there's arguments between, scientists like, oh, what is more fundamental to the universe, whether or not it's the charge themselves, right? The electrons or protons, right, that exist. But some people argue that the fields they create is actually more fundamental because, right, if you have a bunch of electrons here, you wouldn't even know they existed if not for the field they create, right? That cause you, if you put a proton here, it'll be attracted to it, right? You never actually see the electrons themselves. You feel their effect, right? So therefore, is the field the fundamental thing about these things in the universe, or is it actually these little particles, right, themselves? So this is so just like on the textbook, right? There's this thing called plasma ball, and plasma ball worked on a pretty simple principle where it produces an electric field. I think it goes outward. Sorry, actually it goes inward. I think the electric field goes inward. So it's actually a bunch of negative charge in that red part inside the center there. Okay, so if you put a bunch of red charge in the center, right, a bunch of charges and negative charge in the center, it'll create an electric field pointing towards it. Right, so we can actually draw that. Let's draw that in red. Okay, so that's the electric field map around our little plasma ball. Okay, and actually what's happening inside, the reason you see light is because they're actually kind of plasmatized electrons inside this ball. So there's just a bunch of electrons inside, okay? So when you put an electron inside this field, let's say you put a little negative charge there, okay? Actually, if you put it right here in the middle, right, which way would it accelerate? Anyone, which way the force will be applied to it? Inward or outward? Anyone venture a guess? Outward, right? Because electrons, right, the force is actually the charge times the electric field. Since this charge is negative, right, it's actually going to go the opposite direction of the electric field. Okay, so what's happening is that these electrons are flying into the glass, right? When it hits the glass, it just kind of gets stuck there. Okay, and that's why you see these little kind of beams of not beams, but little swirls of light coming out. And the reason you see the light is because as the electrons get accelerated outward, it hits other gases in there and it just kind of lights up that gas. Okay, it's kind of basically the same way that the fluorescent tube works, okay? Right, and right now it's kind of it's kind of like all over the globe. So it just hits, in different places. If I was to touch it, this is why people like this thing, right? What did I do? Why is it when I touch it, now most of the electrons are actually flying through one path? Why do you think that is? Anyone wants to venture? I'm sorry? Well, I'm neutral actually, right? Unless I'm rubbing my feet against the rug a lot. But I'm a human is not, is what? Is it an insulator or a conductor? I'm sorry? A conductor, right? So when there's nothing connected to the glass, right, it doesn't have a preferential path to go to ground, right? But once I touch it, now all the electrons are actually flowing through me, onto ground. Right? That's sort of the neat thing about these little plasma balls. Okay, the electrons actually have an easier path to get to ground as opposed to just a random path. Okay, and it's the same that while this electric field is all around this this globe, right? How do I show that? Actually, do you mind turning off the light in the back there? Sorry, I think there's a switch. Just push down on it. Okay. Yeah, there it goes. Thank you. Well, that's actually really bright, but hopefully you guys can see this, right? The electric field actually exists even beyond the globe, right? Hopefully you guys can see the little one, the fluorescent tube light up, right? And that's because, right, the electric field actually extends beyond this globe and now it's penetrating through this little fluorescent tube. And when the field penetrates through the fluorescent tube, it accelerates the electrons inside the fluorescent tube also, therefore making it hit a bunch of gas particle inside there. And that's basically the principle that your fluorescent tube works on, where you just accelerate the electrons and they hit gas and they deposit that energy into the gas and it lights up for you. Okay. You mind turning the lights back on? Thank you. All right. Does that make sense? There are other tubes also you can do. So after class, if you want, actually today is not a good time. Maybe tomorrow during our discussion, you guys can play around with this a little bit more. Okay. So hopefully that makes sense. Why electric fields are, you know, some people argue that it's actually a more fundamental thing to learn versus the particle versus learning, instead of learning about electrons, we should learn about the fields that these electrons produces. Okay. So as introduced from last time, right? The electric field can be calculated if you just take the charge that the electric field is coming from. Sorry, the electric field is coming from. So let's say you have a positive charge here in the middle and it has some positive charge Q, right? If you want to calculate the electric field from it, right, at some point, let's say 0.1 P1, okay, you need to know the distance R away from it, okay? And the electric field is going to be pointed away from the positive charge, right? So this red thing is the electric field, okay? So it points in the same direction as this R vector, right? Okay. And the magnitude is calculated by the charge divided times 1/4 pi epsilon naught. And whenever you see 1/4 pi epsilon naught, you should just replace, you can replace it with K, right? You don't have to punch all that stuff into your calculator. But we're going to see that why this 1/4 pi epsilon naught is actually an easier value to work with in the future. Okay, divided by the distance square, whatever the magnitude of this is, in the r hat direction, right? So that's how you calculate the electric field from a single point charge, right? And as we illustrated from last time, right, a positive charge, right? Just imagine if you put a positive charge around another positive charge, they will push each other apart, right? So therefore, the force is going to be going away from the positive charge, okay? So therefore, the electric field is also going away from the positive charge. But if you were to put a positive charge near a negative charge, right, they would attract each other, so they would go towards each other, right? Therefore, when you have a negative charge, the electric field actually points in the same direction as that electric force, and therefore it actually points towards the center of that negative charge. Okay, this is just a signage situation. Okay, so when we want to calculate electric fields of multiple charges, okay, just like the way we calculate forces with multiple force sources, right? You have to add them up vectorially, okay? And what we do is we're going to create a coordinate system. So this is sort of like the information gathering part of usually the problems I have you guys do in the worksheet, okay? And identify this point P where you actually want to calculate the electric field. So let's say I'm going to have a coordinate system, some XY system, right? Okay. And a lot of times I would put the charge in the center of it, right? Whatever that charge happens to be, right? And we want to calculate, you know, let's say the electric field at this point P here, right? And so you draw that, okay? And the electric field, this is very important. A lot of times people mistake this, okay? If I want to figure out the electric field at point P, okay, I start the vector of electric field at point P. I don't start it at the charge, okay, right? Even though there is electric field going around all around the charge, the only electric field I'm concerned with is the one that's at point P, right? I want to figure out if I put a charge, a positive charge there, how much force will it feel, right? So I'm only concerned with the electric field at point P, okay? Right, because there's like infinite places you can calculate this electric field at, right? So once you have a single electric field, if you have multiple charges, okay? If you have, this is for a single charge, okay? When you have multiple charges, what do we do with if we have multiple vectors that are the same type? What should we do with them? Add them up vectorially, right? Exactly. So if you want to figure out the net electric field, you just sum up all of the little piece of electric field where each I is the ith charge that you're calculating this with, okay? So just so you know, kind of like, oh, if you got an answer that for an electric field value, I think last Thursday we calculated some electric field, it was like 10 to the I think 10 to negative 4 or something like that. But so if you have a wire, so for example, these wires, right? So it's all around our table. The electric field around them is going to be something on the order of like a millinewton per coulomb. So that's the unit for an electric field, to maybe like, you know, a tenth of a newton per coulomb. Okay. And it's nice to understand, see this units. We're going to see that also have a different units later. Newtons per coulomb, meaning how much force would it exert on a positive 1 coulomb charge if you put it there, right? This is what that's telling you, right? Newtons is a unit for a force. Coulomb is a unit for a charge. If I put 1 coulomb of charge here, let me just go back here, right? If I was to put 1 coulomb of charge here, let's draw that in orange, right? 1 coulomb, oops, if I can spell coulomb, of charge here, basically this electric field factor is the same as the force vector, right? Because the electric field is if you multiply the electric field by the charge, you actually get the force, right? If it's 1 coulomb, then it's 1 unit. So therefore, you actually get exactly the same answer, okay? The electric field near the surface of the Earth, just because we're on the surface of the Earth, we also have electric field that's on order 100 to 10,000, okay? And if you go around these little glass tubes here, you're gonna have electric field that's gonna be on the order of like 1,000 to 1,000,000, okay? If you see a arc, meaning like, let's say, anyone ever like plug in like their laptop charger and then there's just a spark, right? Those are actually electrical sparks or arc, meaning like basically lightning. Those are going to be like millions of newtons per coulomb, okay? The stuff that's actually holding the electrons to the protons inside the atoms are actually on the order of about 100 billion newtons per coulomb. So there's an extremely large force that holds these electrons to the nucleus, okay? So let's do an example where we're going to have to deal with multiple charges, okay? Where we're trying to calculate the electric field from 3 different charges and then add them up, okay? In fact, I'm going to grab my little cheat sheet so I make sure I'm doing it the simplest way possible as opposed to the most complicated way, okay? So in this little example here, 23.1, we have 3 different charges, okay? And each of them have different amount of electric charges on them. Oh, 3 equal charges on them, so they all have the same charge, okay? And we want to try to figure out, that's all on the y-axis, we want to figure out what is the electric field at some distance R2 on the x-axis, right? Where the middle charge here, RQ2, is actually on the x-axis. Okay. So So the information gathering is nice because the book kind of does a little bit for you, right? So we just want to make sure you do this drawing, X and Y axis, right? Place your charges where the problem describes where they're placed, okay? And then draw some point P, okay? I'm just going to draw this point P over again, where even though it doesn't tell you what the number R2 is, right? It could be actually a negative number, right? Right? But just place it somewhere so you have a way to just draw the diagram, okay? Because it doesn't actually tell you what R2 is, because they just asked you for what is the electric field at a point, okay? So you actually have to declare this R2, okay? Okay, so at some point on the x-axis, okay? So the strategy is that, well, the concept is that we want to calculate the net electric field. You can just do E field, right, by adding the E fields, that's plural, from how many charges do we have? We're going to have to add how many E fields together? 3, right? From 3 charge. Well, specifically, they're actually point charges, okay? Because they don't have a, it's not a rod, it's not a sheet, it's not a sphere, okay? Even though they're drawn as sphere, they're just assumed to be these point charges, okay? All right. So the equation we're going to start with to solve this thing, right, is that the electric field is going to be 1/4 pi epsilon naught, the charge, each of the individual charge divided by r squared in the r hat direction. That's what we have to start with, okay? So we're going to have to figure out the r's for all this. The charges are all the same, so we're just going to call it, Q1 equals to Q2 equals to Q3. We're just going to call that Q, okay? Just so we have a value to assign it. It's just so we have a variable, okay? But by looking at, since these two charges are the same, but then they go towards this point, right? Right? What do you guys think the y direction of the electric field is going to be if you have these two charges on the opposite side of the x-axis, right, going in the same direction? They're going to add up to 0, right? So all we have to do is actually figure out the x component, right? We don't have to do the y component, okay? So the net electric field, that's not a vector, in the y direction is equal to 0 from the symmetry of the problem. Okay, does that make sense to everyone? Where you have this vector going up, you have this vector going down. The y component of these are going to be equal and opposite each other, so they add up to 0, right? And then charge number 2 has no y component, right? So all we have to do is figure out the x component, okay? So let's do that one at a time. So electric field from charge number 1, the x component is the magnitude of that electric field, okay? And I'm going to declare an angle called theta here, okay? So actually, this theta, right? So if we want the x component, right, that's just the adjacent piece. So therefore, right, that's going to be cosine of theta, okay? All right. The magnitude of the electric field is given by this equation here, but we're going to have to figure out what R1 is. So go back to my orange, okay? So 1/4 pi epsilon naught, okay? Q, which is all the same for everybody. And instead of putting R, I'm going to put R1, okay? Because that's the distance from charge 1 to my point P. That's what I'm going to call it, okay? Oops, forgot the square. Of course, I also forgot to multiply that cosine of theta. Okay. So before, trying to jump into this, cosine of theta, right? There's this angle here, right? By, what is this called? Like the opposite angles are the same as each other, right? In that, right? This angle is also theta, right? Because this is a straight line, this is a straight line, so this makes the same angle. So you can use this similar triangle situation where, well, theta, right? If I want cosine of theta, I can take this adjacent over the hypotenuse, right? So cosine of theta, I'm going to copy all of this over 1 square. It's the adjacent piece divided by the hypotenuse, right? Right. And then the adjacent is actually this distance R2, right? And then the hypotenuse is actually R3. So this ratio is actually R2 over not R3, R1. R2 over R1. You see that? This ratio, right? That's that adjacent over the hypotenuse will give us the cosine, right? And then R2 over R1 will give us cosine of theta. Okay. So therefore, this long equation gets even, well, it doesn't get too much shorter, but it does shrink a little bit, R2. So you have one factor of R1 here, two factors of R1 one here, so it's R1 to the third power. Okay. R1 is also another value. Okay. R1 is actually the hypotenuse, right? So therefore, you can use Pythagorean theorem. So the distance between the charges is D. The distance out to the point P is R2, right? So therefore, R1 is actually just x squared plus D squared because this is the hypotenuse. So you take this square, you take this square, you square root the whole thing. Then you get to, right, where x is actually where how far away from you are on the x-axis. This is the x position of the position P, okay? So that's one of the things that's confusing, right? This is, x is not only the axis, it's the value that on the x-axis you have, how far away are you from it, okay? You can call it x prime, you can call it px or something like that, whatever you want, but the book decided to just call it x, okay? So we do all this substitution where R2 is actually equals to x, right? Put all the stuff in there. You have charge, you have x on top, and then you have x squared plus D squared to the 3/2 power. Okay, everyone okay with me getting that 3/2 power? Okay, when you have a square root, it's the same thing as writing 1/2 power, right? If you have, so R1 is this to the 1/2 power, right? When you take it to the third power, it just goes in the numerator. Okay, so that's actually E1 in the x direction. And from the symmetry of the problem, going back up here, right? The x component of E1 is going to be, how's it going to compare to the x component of E3? Equal to each other, they're the same, right? So we don't have to calculate this 2 times, okay? Right, but we do have to calculate E2 in the x direction. Fortunately, E2 has a simpler geometry, right? E2, right, is just exactly distance x away from charge number 2, okay? So that's just 1 over 4 pi epsilon naught q divided by x squared, right? And that's it. Are we okay? Right? Anyone want to tell me why there isn't this complicated square root and all that crap in E2 situation? Right? It's just straight. You don't have to deal with the cosine theta thing, right? You don't have to deal with Pythagorean theorem. You don't have to figure out this distance, right? This distance is actually exactly x, right? You don't have to do anything. Okay. So now, right, to get the net electric field, you have to add all these things up together. Okay. Right. I'm going to do the vector version. Okay. And I know that the electric field is only in the x direction, so it's all in the I hat direction. That 1 over 4 pi epsilon naught, I'm just going to copy it twice. It's fine. It's a good wrist exercise, let's say. X over x squared plus D squared to the 3/2 power. Since I'm going to add here, actually, let me do this. Sorry, go back one step. I'm sorry about that. Because what I'm doing, I just want to show you guys, right? is it is in the I hat direction. I'm adding up the electric field from 1 plus the electric field from 2 plus the electric field from 3, right? I'm adding all 3 of these together. If I add these 2 together, right, I would just get twice the electric field, right? Because they're the same. So therefore, these 2 guys, oops, 1 and 3, is just 2 times this, okay? So 1 over 4 pi epsilon naught, 2 times qx over x squared plus d squared, 3/2 power. And then this piece here, right, it's also 1 over 4 pi epsilon naught, q over x squared, okay? Okay. If you simplify this in combined terms, you'll end up with this answer here, where it's 1 over 4 pi, sorry, q, well, 1 over 4 pi epsilon naught times q, right? This 1 over x squared, right, is from this term, right? If you factor out this, right, you just have 1 over x squared. The second term here is the the one with the 3/2 power, okay? Thanks. So that's how you calculate the electric field from 3 different charges, okay? Any questions about that? You just plug it in. Well, we use the electric field equation twice because we know that E1 and E3 are the same in the x direction. And then E2 is pretty simple, right? Right. So you want to look for these simple ways to do it. Yeah, Cole?
So P, we can choose to be as big or as small as we want.
I'm sorry?
We choose the value of P, right?
Well, we keep the value. So the value of P is, there's no value. P is signifying the point where you want to figure out the electric field. And the book in this case decided P, the position of where P is. So let me draw my x-axis. Oops. Right. My 3 charges are like this, right? And the book say, oh, calculate the electric field at some point P. Okay, yeah, so P can be, you know, really close, right? Or really far away, but we don't know, right? So we're just gonna declare that, well, the distance to P from the y-axis is just x, okay?
Yeah,
that's what,
yeah.
Yeah. So, and yeah, D is the distance between the charges, okay? So this is given, this is given, this is given, and your answer has to be in all the values that are in the variables that are given, okay? Okay. All right, so let's do the limiting case, which is kind of interesting, okay? So on the drawing on the right here, right, I drew X very far away. So therefore, right, meaning X is actually much bigger than D, okay? If X is much bigger than D, okay, we take this, this formula here that we derived just now, right? That means X here is much bigger than D here, right? So if you take 2 numbers, square it, but one is much bigger than the other, the X is actually the thing that matters, right? The D doesn't actually contribute that much, right? So let's say I want to calculate 100 square plus 1 square, right? The result is going to be basically like 100 square. It's going to be like 10,000, right? Because 1 square is just 1. 100 square, right, is 10,000. 10,000 plus 1 is approximately 10,000, right? So you're not going to care about that. Okay. So therefore, when you do this, right, you get approximately q over 4 pi epsilon naught, 1 over x squared plus 2x divided by x squared plus something small, but you don't care about that, to the 3/2 power, okay? So when you take power to the power, you basically are like multiplying them together. So 2 times 3/2 is basically 3, okay? Then I'll rewrite this again. This is actually an equal sign now, 4 pi epsilon naught. Sorry for the bad epsilon, I'm trying to be lazy, I think, okay? So 1/2 x squared on top. You have 2x divided by x to the 3rd. That simplifies even more because you can take them and divide by each other, right? So here you have 2 over x squared. You have 1 over x squared here. They have a common denominator, so you can add them together. So this is actually 3x divided by 4 pi epsilon naught. Oops, no x's over x squared. So that's the limiting case. Okay? That's what is on equation 23.5. Okay. So one of the things is that, well, if the three charges, let's go back up here, right? If these three charges, right, the distance d is much smaller than x, meaning this, we're like really, really, really far away, right? Those three charges looks like as if they're together, right? So this is something that you have, you may have experienced in real life, right? Where you have, let's say you have three people walking towards you from far away. They just kind of look like, one lump together, right? Right. So you don't see the individual, but you see all three charges still. Okay. And that's from having 3 times that charge. Okay. So here you have you have a graph of how these, how the electric field behave as a function of D. And it's just, I think having the different graphs is not extremely useful. But one thing to note is that the electric field, right, of something, right, is proportional. It's always going to be proportional to kind of 1 over r squared. Okay. And basically, it looks 1 over r squared graph looks like this, where it just dips down really quick and kind of approaches 0 as you go to infinity. Okay. This is, be a little careful. A lot of people think, oh, that looks like an exponential decay. It's not an exponential decay. It's a 1 over r squared law. Okay, drop. Okay. Any questions about these 3 charge electric field calculation situations? A lot of triangles involved, right? A lot of square roots, and then taking care of powers, and then adding things up vectorially. You have to add the x component, you have to add the y component. In this case, we didn't have to deal with the y component because we know it add up to 0, right? All right. Let's keep going. So I'm not going to do the derivation for the dipole because it's a very similar thing than what we just did. But for example, this is very useful when you're trying to calculate the effect of an electric field that's actually created by what's known as a dipole, meaning you have something that has a positive charge on one end and a negative charge on the other end, right? The previous example, we had 3 charges that are all pluses, but for example, water, right? Water is a polarized molecule. So the ends that holds the hydrogen usually have more positive charge, has a slight positive charge, where the ends with the oxygen has a slight negative charge. So if you kind of zoom out, you're very far away from the water. So usually you're not staring at a single water molecule, right? You're pretty far away from the water, right? It will look like this situation where you have a dipole where it actually creates an electric field from the negative to the positive. Be a little bit careful, okay? Because usually you're thinking about electric field coming from positive to negative. But if you were to zoom out very far away, it'll actually look like an electric field going upward. Okay. And this is actually what makes water an extremely special molecule. Okay. The fact that it's a highly polarizable molecule makes it, first of all, liquid. Because usually when you have molecules that has the atomic mass of about 18, which water is, it's usually gas. Right? So like oxygen has an atomic mass of 32, nitrogen 28. Those are gases, right? They're just floating around. Okay. But water, even though it's lighter, somehow it's liquid, right? At room temperature. And the reason for that is because it's highly polarizable. So these electric fields are interacting with each other and causing them to liquefy. And we don't have enough time to describe why this happened. You can take either more chemistry classes or thermal physics. And you can actually figure out why water is liquid. And that's why you have water to drink at room temperature. You don't have to be at minus 50 degrees in order to have water, liquid water. Okay. So the calculated dipole, I'm not going to go through the calculation, so you should follow it on the textbook, because it's going to take me another half an hour to do that. The electric field from a dipole, if we're calculating the electric field, right, on the x-axis, just like the same way we did before, okay? This is 1/4 pi epsilon thing again that you have to write over and over and over again. Multiply by 2 times P over R to the third. What the heck is P? P is the dipole moment. Okay. Okay. Of that molecule, of the molecule. Okay. Okay. And you can calculate that. Where is it? It's up here somewhere. Okay. Sorry. And you can calculate that by just taking the charge at each of the end and multiplying by the distance s between them, this x vector. Okay. Right. Basically taking the charge, just the charge on one end, and multiplying by the distance between the two things. Okay. Actually, a lot of times you just care about the magnitude. So, okay. So as I said, the dipole moment of water is pretty big. Ethanol is smaller. There are other organic solvents that also have a much bigger dipole moment because they're very highly polarizable molecules. So you don't have to go through all of these different chemicals. We're not going to test you on it, but it's just a useful thing to know that the reason that water exists in liquid at room temperature is because of the polarizability slash what we call the dipole moment of water. Okay. Yeah, let's not go through the other types of dipole moment. Okay. Why isn't this refreshing? There it goes. Okay. Okay, so before we wrap up today, I just want to give you guys a little lesson on how to draw electric field lines. So we've been talking about this electric field thing, but a lot of times it's nice to visualize it, right? Therefore, you can actually draw a picture. And then when you do your calculation, right, let's say your electric field line is going to go in this direction, but then when you calculate it, it goes downward, you know something went wrong, right? So how do we draw these things? Okay. So we kind of already know how an electric field line looks like if you have only a positive charge or only a negative charge, right? When you have only a positive charge, they all point away, kind of like spikes, right? Kind of like a porcupine situation. If you have negative charge, I don't know what reverse of a porcupine is, but everything points towards it, okay? Right? So first rule is that, right? The field lines always emanate, meaning going outward from positive charge, but then it ends on a negative charge, okay? The second rule is that the electric field line can never cross each other, okay? The reason they cannot never cross each other, remember that electric field, right? If you have electric field, you can actually calculate the electric force, right? By just multiplying the test charge. So you can even to put QT here, right? So if you have an electric field that actually crosses each other, if I was to put my QT here, right, it's like it's like telling this charge, okay, you have to go in this direction and this direction at the same time, right? That doesn't make any sense, right? So they should never cross each other. You should never have an electric field line that points at a single point that points in two different directions, right? Right. So this should never happen, okay? So that's bad if you did that, okay? So if we have a dipole, meaning you have one positive charge and one negative charge, right? How should those electric field look like, okay? So the first thing is that, well, the field is going to emanate from the positive charge, but then it has to end on the negative charge, right? Okay. So maybe the first simplest one is that the one that goes straight like this, right? So that's a valid electric field line, okay? But what if there's one, you know, the field line also emanates outward from here, right? Right, from the top, from outward from here. But we know that that field line has to end up here on the negative charge, right? So all I'm going to do is I'm going to connect them through some, you know, nice smooth curve, right? That's all you need to do. Okay. The ones in between, right? It's kind of like this. Okay. You got more field lines going like this. You can draw as many as you want. Okay. But what about the ones that are like, you know, maybe coming out here, but slightly upward? Okay. Where would it end up? Go all, yeah. It's kind of like this I don't know what shape this is, kind of like a little walnut shape situation, or right, or like an apple that's cut in half, right? And when you're drawing the electric field line, make sure you point the arrow, right, as much as you can, because, right, if I put a positive charge here, I need to know that it's going to go to the right, not to the left, right? If you didn't put the arrows there, right, it could go to the left or right. Okay. All right. So that's what. So whenever you have a problem, you want to draw these field lines just so you get a sense of what the problem is will end up looking like when you actually do the calculations by hand. Okay. All right. So we've got another 5 minutes. So I'm going to introduce this topic, but not go through it. So we'll finish it up tomorrow. So far we calculated electric field from point charges, but a lot of times charges are not point charges, right? You're going to have a continuum of charge of like maybe like this shape, right? Or sphere shape or plane like a table. In real life, electric charges is probably more complicated, like human shape, right? But one thing that's kind of neat about the rod, the sphere, and the plane is that like people are actually just combinations of those things. Kind of a weird, not exactly a spherical sphere, but pretty close, right? Plane, you can model my arm as a stick, right? So if you can calculate the electric field from a rod, a sphere, and a plane, you can actually do it for any shape by superpositioning them or adding all these electric fields together, right? Right. So if you model a human as a plane with a sphere and a bunch of sticks, you can actually build a person that way, right? So that's why I want to learn how to calculate these. And these electric fields, we can actually calculate fairly easily, meaning within like 20 minutes of me struggling with calculus type of calculations. So we're not going to do that today. We'll do that tomorrow. Okay. But let me just introduce the techniques on how we're going to deal with it. So on a stick, right? This is probably like the simplest geometry. Okay. Where let's say you have a bunch of plus charges and in all these problems, you just assume that the charge is positive. If it happens to be negative, right, you just put a negative sign in front of the answer, right? That's the only difference. Okay. You just assume that it's a positive charge. Okay. Since you have a bunch of positive charges, right? And this rod has a length L, right? The total charge, Q, that's the total charge, right? If you have a total charge of Q distributed on some rod that has a length L, right? What we're going to do is we're going to have this thing called the charge density, meaning how much charge is there on each pieces of the rod, right? And to calculate that, it should be pretty simple. The charge density is represented by this symbol lambda, charge density, just a lot of Greek letters, right? It's just the total charge divided by the length of that rod, right? That's how you figure out how much charge is there per length, okay? And we're gonna have to deal with this delta L thing in a second, okay? So that's one thing to note, okay? On a sheet, okay, so this is the way the book covers it, right? So instead of getting charge per length, you're interested in charge per area, right? So let's say this table has like 10 coulombs of charge, right? How much charge is there per little area on this, okay? On this little table, okay? So in this case, right, we're gonna have a charge density per area, okay? So there's the length charge density. Now there's an area charge density. Guess what we're gonna have next though, okay? So the area charge density, right, is gonna have this Greek letter eta, okay? So the way I write this is just to kind of have like an N that has an extra long tail to it, right? It's just the amount of charge per area, okay? And has units of, since it's a charge on top, let's have a unit of coulombs on top. And then since down here is area, what type of units, what's the SI units for an area? Meter square, right? Exactly, right? Right, just imagine a square, literally a square. If it's 1 meter here, 1 meter here, you multiply those two numbers together, this is 1 meter square of area. Okay. And we'll talk about how we're gonna use these charge density in order to do calculations with either rods or plane. And since I have maybe like a minute left, I'll do the same thing with the sphere. So let's say you have a sphere, right? And you have a bunch of plus charges in the sphere. But I want to figure out a little box here. How much charge is there per volume? Per volume, okay? What I'm going to do is I'm going to take the, and this is going to be a letter rho, RHO, okay? And that's the amount of charge per volume. And this is where it's kind of funky, right? If it's a sphere, then you have to figure out, you have to know what the volume of a sphere is. Volume of a sphere, right, is going to be 4/3 pi r cubed, right? But let's say if you want to figure out the volume of just a cube, right, that's going to be the length of its square, to the third power, not square, right? So depending on the shape that you're dealing with, you're going to have different V's, different volumes on the bottom, right? And of course, this will have units of coulombs per meter to what power now? Third power, yeah, exactly. Okay. So that's sort of an introduction to kind of the geometry we're going to have to deal with. And we're going to go through how we can do this with the little calculus thing that you might have seen in Calc 2, but we're going to go through those again together anyway. Okay. So I'll see you tomorrow. Turn to the meeting.